Moving on in our physics lessons, we will now talk about dynamics, which means forces, a few different kinds of forces, and Newton's laws of motion and how those forces cause a change in our current state of motion. So notes 12AB, dynamics. There is math in here, so get ready. Here we go. What kinds of forces are we talking about? Well, we have two main categories that you'll see on the next page. But the definition of a force is any push or pull on an object. Now, pushing and pulling on an object may not cause motion to happen, as you see there. A push or a pull or a force may cause motion to happen, but not always. The force has to be strong enough to overcome a property we call inertia. We'll talk about that in just a little bit. Dynamics is the study of forces and how forces change motion. If we want an object to change its current state of motion, change direction, speed up or slow down, or take something not moving and put that object into motion, we have to know about forces, balanced and unbalanced. Remember what vectors are. Vectors are measurements that have a magnitude and direction. Force is a vector. And with the force, we call the magnitude the strength of the vector, how strong the force is. And forces are also directions, therefore forces are vectors. The direction of the net force will determine the kind of motion that we get. Force is a vector. We measure force in the metric system with a unit called Newton. I'll bet you can guess who that's named after. He sat under a tree, an apple fell on his head. You probably guessed it, Sir Isaac Newton. Lowercase n if you write out the whole word, capital N if you use just the abbreviation. A Newton is defined as the force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second squared, gaining 1 meter per second of speed for every second of time that we apply the force. So a Newton is the force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. A Newton, because of the definition, we see that the Newton is actually a kilogram meter per second squared. That little asterisk thing, that's the computer's symbol for multiply. So it's kilogram times meters per second squared. In the English system, we're a little more familiar with this as a pound. And we usually use pounds when we're talking about weight, but weight is just one kind of force. So a pound is used in the English system to measure any force, but in the metric system, it is a Newton. Ready? Contact and field forces, two main categories. And contact is what you might expect. Forces are applied when these objects touch each other or collide, such as, again, the world's greatest sport. A baseball makes contact with a bat. The ball's thrown, we swing the bat, we make contact, and we apply forces, and we actually transfer other things such as energy and momentum, which are coming later. But contact forces happen anytime objects touch or collide. The other kind is called a field force. And these forces can be applied without the objects having to touch each other. For example, put two magnets close enough together. The like poles, if we have two north poles or two south poles close enough together, those poles will repel each other, push those magnets apart from each other. Or if we have unlike poles, a north and a south, we don't have to touch the magnets to get those magnets to attract. We just have to get them close enough to each other, and then the force of attraction will occur. Same idea with static electricity. We've talked before about protons and electrons. Like charges repel, unlike charges attract. Well, that's static electricity, which is also a field force. A downed power line, if we get too close, don't touch those things because they're extremely dangerous and even deadly, but we may be able to feel some of that electric energy rush into our bodies. That's an electric force, a field force, without having to touch. Contact forces, when objects touch. Field forces happen without the objects touching each other. Ready? Balanced and unbalanced forces. What do we mean by that? Well, consider sitting on the chair. Lift your feet up off the ground and notice the chair is holding you up. You're not going through. The force of your weight putting onto the chair is balanced by the chair's force pushing back up on your body. And we'll talk about that when we hit Newton's third law of motion later on. There are always multiple forces acting on all objects. If there's no motion, well, that means all the forces are balanced. The forces cancel each other, so there's no current change in the motion. I said that poorly. No change in the current state of motion. I want you to emphasize the word change in this definition. Notice that I highlighted that because here's why. Objects that are not moving, we can easily see that forces are balanced because there's no motion. However, think of an object moving at a constant velocity, staying at the same speed in the same direction. Are the forces acting on that object balanced? The answer is yes, because there's no change in the state of motion. So moving objects can have balanced forces if these objects maintain the same velocity, same speed and direction. It takes an unbalanced force to cause any change in the current state of motion. So to get an object sitting on the table to move, I have to apply some kind of a force, likely lift the object, push the object, or whatever. A rolling ball, if I want that ball to stop, put my foot in front of that ball and apply a force to make that ball stop. Now the ball rolling along the floor, especially a carpeted floor, will eventually stop on its own because there's a force called friction pushing back on the ball, applying an unbalanced force. Balanced forces cancel each other, no change in the motion. Stationary object undergoes balanced forces, and an object moving at a constant velocity, same speed and direction, is also under balanced forces. Anything that's accelerating or decelerating, changing either speed or direction or both, is undergoing unbalanced forces. So let me quickly write that up here. Balanced forces are when we have a constant velocity, no change in speed or direction. Unbalanced forces means that acceleration has occurred because we have changed either the speed or the direction, which means a change in velocity. Ready? Now look at the pictures here. Force vector diagrams. These will help us see what's going on. I'm going to start with the tug of war down here. Okay? You got the two teams pulling. Now, hopefully you can see the numbers okay. The blue team on the left is pulling to the left. In case you can't see the numbers, I'll write that here. With 2,200 total newtons of force. The green team here on the right is pulling to the right at 2,500 newtons of force. Which team's going to win? This is one of those, duh, the team pulling with a stronger force will end up winning. How much stronger is 2,500 newtons than 2,200 newtons? Pretty obvious, just subtract. We have 300 newtons of net force going to the right by subtracting these two numbers here. So the green team, that's what this word says, in case you can't see it, that team's going to win. Okay, now let's come over here. Look at the top right here. I have one person pulling with 1 newton of force, which is a very small amount, by the way, and another person pulling in the same direction with 1.5 newtons of force. Well, look what happens here. Okay, we add these together. This says 2.5 newtons. So I have 1 newton plus 1.5 newtons going in the same direction. That equals 2.5 newtons of force. Okay? All right, I'm going to clear this off. I'm going to change colors so you can see this a little better. Notice that the 1 newton of force to the left plus 1.5 newtons of force to the left, that's 2.5 newtons going to the left and 1.5 newtons going to the right. Since these are in opposite directions, we're going to subtract these. 2.5 minus 1.5, that's going to give us what? It's going to give us 1.0 newtons. But which direction will this block end up moving? Which one is stronger? Again, it's a common sense, but we can easily overlook the obvious. The math verifies common sense. I will say that a lot in these physics chapters. And you see right here, 1 Newton of force going to the left, and on the top, because these are going the same direction, we simply add them together and we get the 2.5 newtons. Now look at the bottom right here. I want you to notice something. We have 30 newtons going north and 40 newtons going east. How are we going to figure this out? Like, where'd that 50 come from? Well, notice here we have a right triangle. So, as we've said before, your good friend, Mr. Pythagorean theorem. C squared equals 30 squared plus 40 squared. And if we go through the math, we're going to end up with 50, and then put the unit in the final answer. The block is going to go northeast, but will it be a little more toward the north or a little more toward the east? We can tell because 40 is greater than 30, so this object is not at a 45-degree angle going up here, because this force is a little stronger. That's being skewed a little bit more toward the east. We'll have practice problems with these. Okay, now the notes. Force vector diagrams show all the forces and give us the net resultant. In each of these examples, we got the net resultant, 2.5 newtons here, 1 plus 1.5, 1 newton to the left here, because 2.5 total left, 1.5 to the right, and you saw the math, and then the Pythagorean theorem gave us 50 newtons to the northeast, 30 north, 40 east, 50 northeast. The object will end up moving in the direction of the net force, the result after we add everything together. Now remember, like velocity, forces are vectors. The motion that is desired is considered the positive, so the opposite is considered the negative. So that's why I can say we add these together. This will just be adding a negative 1.5 because we're going to the left. Ready? Inertia, I mentioned this a little while ago. Inertia is a change in the current motion. Let me say that again. I forgot the word resistance. Inertia is a resistance to a change in a current state of motion. Here's something that's common sense, but now you see scientifically. Think of a soccer ball and a bowling ball, both being the same size. Obviously, we know they're much different weights. A bowling ball can weigh as much as 16 pounds. I would not want to try to use a bowling ball to do a penalty kick. Which one would be easier to move with a kick? The soccer ball or the bowling ball? Well, the soccer ball weighs a lot less because the soccer ball has a lot less mass. So the soccer ball has less inertia. We can change that motion, which would be standing still, much more easily. Now, try to kick that bowling ball, you're going to hurt yourself. That's because larger masses, not necessarily larger volumes, larger mass means more inertia, more resistance to a change in the state of motion. That ball sitting still, not moving, that's the current state of motion, no motion. If I have a very light object, such as a soccer ball, a small force applied can get that ball to move. But just barely tap the soccer ball and barely tap the bowling ball. Which one will move further and faster? The soccer ball will, because the soccer ball has less mass, so less inertia. The bowling ball has more mass, so more inertia. Well, larger velocity. If I take a tennis ball and just toss it to someone, very light toss, that ball would be easy to catch. But if I took that same tennis ball, same mass, and threw that ball a lot harder, that ball would be much more difficult to catch. That's because moving inertia is larger when the object has larger velocity. Now, the two of these together, mass and velocity, you'll see in a little bit, those make up something we call momentum. Common sense, but now you're seeing scientifically. All right, think of a BB coming out of a BB gun. If I just toss a BB at somebody, no big deal. But if I were to shoot that BB at a tree, then that BB may embed itself in the tree if that very small mass is moving fast enough. And these are, again, are things that you know common sense wise, but now you see scientifically. Unbalanced forces may overcome inertia and cause motion. Now notice I highlighted the word may. Think of this. I have that bowling ball on the ground. I can tap that ball, but if I don't tap that ball hard enough, that ball's not moving. So the force has to be unbalanced and strong enough to overcome the object's inertia in order to cause a change. A faster moving object, think of driving a car. If I drive a car, I can go around a sharp turn very slowly and safely and very easily. But if I'm going fast around that same sharp turn, that will make very difficult control of that vehicle while I'm going around that sharp curve. That's because even though both cars are the same mass in both situations, the faster moving car, larger velocity, has a lot more inertia. Ready? Now, Sir Isaac Newton came up with 3 laws of motion that you'll see in word form. And if you look at or listen to the words, they can sound a lot more complicated than they really are. But then just think about it, and again, common sense. Now, the second law of motion has a math formula I'll talk to you about in just a bit. Newton's first law of motion, I broke this up into sections. It's really all one sentence. Objects in motion will stay in motion. Let's say we're in outer space where there's no friction or resistant forces of any kind, and I throw that tennis ball. That tennis ball will move in a straight line at the same speed forever, or until getting into some large body's gravitational field. Objects in motion will stay in motion. Objects at rest will stay at rest. Think of that bowling ball again, or the soccer ball. When will either of those balls move? If nothing pushes on those balls hard enough to overcome the inertia, well then those soccer ball and bowling ball will not move. Those objects will stay at rest because there wasn't a strong enough outside unbalanced force. So I really should have put strong enough outside unbalanced force. Whether the object is moving or stationary, whatever the object is doing will keep happening until an unbalanced force causes a change in motion. That's the summary of the property of inertia. So we can say inertia summarizes the first law. The object at rest will stay at rest, and the object in motion will stay in motion until acted upon by a strong enough outside unbalanced force. That's Newton's first law of motion. Look at each part, and again, common sense will take over. Ready? Oh, I sometimes forget there's a bottom line on there. Think of in the seat, with the car, with the seatbelt on. Have to hit the brakes really quickly, really hard. Well, because our bodies are moving, our bodies are not attached to the car. So without the seatbelt, our bodies would be thrust forward into the dashboard or the steering wheel or the windshield, and you're looking at potential serious problems or even death. The seatbelt is made to grab our bodies and keep our bodies in place because our bodies have moving inertia. So when we hit the brakes on the car may stop quickly. We have to keep it under control, but our bodies want to keep going forward. Something has to hold our bodies in place. The seatbelt pushes back on the body that's trying to go forward. The seatbelt will push back. Now ready. Newton's second law of motion. Now the words are going to look pretty weird at first, but again, think about it, common sense. Here in word form, the acceleration of an object is, remember acceleration means changing speeds. So let's think of getting faster. We want an object to go faster. What do we have to do? Obviously, we have to apply a strong enough force to get that object to speed up. The acceleration of an object is directly proportional to the force applied. Again, common sense. If I push a little bit, let's say I have a tennis ball, and I hit that ball with a racket just barely. That ball's not going to go very far. Or hit the baseball with the bat just barely. the ball's not going very far. But if I apply a stronger swing and I hit that ball with more force, the ball should go faster and further if I get it up in the air a little bit. So the acceleration of an object is directly proportional to the force applied and inversely proportional to the object's mass. Now, directly means both quantities do the same thing. So direct proportion means push harder, more force, an increase in both. Think of math class. Inversely means opposites. So if the mass is heavier with a weaker force, I'm going to get less acceleration. Soccer ball, bowling ball, again, tap each one. The less mass soccer ball is going to go further and faster than the heavier, more massive bowling ball will. So inversely proportional means opposites, and again, it's common sense. More force, more motion. Less force, less motion. Now think of mass. More mass, less motion with the same force. Less mass, more motion. Now we are ready for the mathematical formula for Newton's second law of motion. Ready? Here we go. In equation form, A equals F over M. All right, now I will write this up and down. Acceleration equals force over mass. Now let's go through the words again. The acceleration of an object is directly proportional to the force applied. We already know if we increase the top of the fraction, we get a larger answer. So more force, more acceleration. And inversely divide proportional to the object's mass. We already know that if we increase the denominator, the bottom of the fraction, we get a smaller answer. Okay, we already know that. So more mass will give us less acceleration. Now before I put the next line up here, let's do a little math here. Okay? I want to get F all by itself, which means to cancel, I have to do that. Now, F equals M times A, and rewrite that as F equals ma, force equals mass times acceleration. Newton's law of motion is written really this way, but many people tend to remember the equation better like that. Either way is acceptable. So we do a little bit of manipulation to acceleration equals force divided by mass. We get force equals mass times acceleration. And all I did was show you one little manipulation on the math formula simply by multiplying both sides by m to cancel this divide. The units will work out to where force is kilogram times meter per second squared, which you saw earlier. That's called a Newton. Force equals mass times acceleration is the shortened form of Newton's second law of motion. Very quickly in word form once again. The acceleration of an object is directly proportional to the force applied and inversely proportional to the object's mass. In equation form, acceleration equals force divided by mass, or force equals mass times acceleration. Ready? Newton's third law of motion. Look at the rocket. Where does the fuel come out of this rocket? Okay, the fuel is coming out this end here. Newton's third law of motion, you'll see the words in a moment, says every action has an equal and opposite reaction. So if the rocket is pushing all the fuel out straight back, then the rocket will propel itself forward. I mentioned a little while ago sitting on the floor, okay, or sitting on the chair. When we sit on the chair, lift your feet up. Can you feel that the chair is actually pushing up on your body a little bit more strongly than when you have your feet on the floor? That's because with your feet on the floor, we're actually putting less of our weight, so less force on the seat of the chair. But lift up, gravity's pulling down on us the same, but we have less resistance. So there's more force being applied to the chair. We feel that by being pushed up from the chair. Every action has an equal and opposite reaction. No matter what we do, there's something just as strong being put back onto us. When we hit the ball with the bat, okay, have you ever noticed that the bat swings forward but when making contact actually gets pushed back a little bit. This is why the coach says to follow through, continue your swing, so you continue to add more and more force to send that ball, accelerate that ball in the opposite direction. In this picture, the fuel pushing out the back is what propels the rocket forward. So down to the left, like I showed you a moment ago, we'll shoot that rocket up to the right. We can put a balloon on a string and fill up that balloon, and if we let the air out go straight back on the string, then the balloon will propel itself forward all along that string. You ever pushed on the wall? The wall's going to push back on you, and that's why your arms get tired, because that force is coming right back into your body. You're not really expecting that. We want that wall to move. Anytime we push at something, we're expecting to move the object. But again, if we don't apply a strong enough force, we're not causing motion. That wall will push back on us and tire our arms out. Ready? Almost done here. I mentioned this a few minutes ago. Momentum is how much motion the object possesses. Now, a little common sense here. The bowling ball sitting on the ground, not moving. So how much momentum? 0, because no motion means no momentum. And mathematically, you will see why. There you go. Equation, P equals mv. Lowercase p stands for momentum. I forget the word, but the little p comes from the Latin word for momentum. So like some of the chemical symbols on the periodic table, that looks like it doesn't make sense, but that's what we use. Little m is mass and little v is velocity. So momentum is mass times velocity. Now remember, a few minutes ago, we talked about inertia, mass, and velocity. An object that has more mass has more inertia. An object that has more velocity, this object's moving, has more inertia. So we're talking about either stationary or moving inertia. Well, a stationary object has no velocity. So it doesn't matter how much mass the object contains. Let's even say 5,000 kilograms. If the object isn't moving, then we're multiplying by 0 meters per second. Well, we know that anything divided by 0 is 0, and I'll tell you the unit that we use for momentum in just a bit. Make sense? Let's say we have a 50 kilogram mass moving at 15 meters per second. How much momentum does this object contain? All we have to do is multiply 50 times 15. We get 750. Here is your unit for momentum, a kilogram meter per second. Now a Newton is a kilogram times a meter per second squared, and someone decided, let's just call that a Newton. We don't have a shortened way to write momentum. The unit for momentum is kilogram meter per second. At first it might look like it's easy to forget, but then remember, mass times velocity. Mass times velocity. So if you forget the unit for momentum, just realize which two units you're multiplying together. A little common sense here. If I have a heavier mass, again, common sense, but the math will verify. Let's say instead of 50, I have 100. 100 kilograms. Well, 100 times 15 is 1,500. So common sense says that if I have a heavier object, that object at the same speed has more momentum. And the math verifies that. Okay, go back to the 50 here, and let's say instead of 15, we're going to do 25 meters per second. Well, what's 50 times 25? All right, 1,000, assuming no mistake, 250. So more speed gives us more momentum, just like more mass and more speed or velocity gives an object more inertia. Well, that's because that object has more momentum. And that would work if I were to lower the numbers too. Again, common sense. Lower times 15, that's 150. So lower mass, lower momentum, or lower speed, lower momentum. So as I'll say many times, math verifies the common sense. Momentum is mass times velocity. Ready? That's the end of this set of notes. There's a lot more coming. And again, there's going to be a lot more math coming. So force yourself to learn. Thank you.